Imagine rewiring our understanding of the very first stars ever to illuminate the cosmos. Stars that may not have all been colossal giants as scientists long believed. For years, astronomers have been piecing together the story of those ancient stars, which played a critical role in creating the chemical elements that enriched the universe and paved the way for planets like ours to eventually form. But here's where it gets controversial. New research now suggests that the earliest stars might have included smaller, less massive members, challenging the long-held idea that they were uniformly massive. Originally, these pioneering stars consisted almost entirely of hydrogen and helium, leftovers from the Big Bang. Conventional wisdom held that they were extraordinarily large, from hundreds to thousands of times the mass of our sun, and emitted dazzling luminosity millions of times greater. Their lives, while spectacular, were also fleeting, ending in massive explosions known as supernovae. Because of that, they had neither the time nor the materials needed to form planets, and these first-generation stars have long since vanished from sight. But recent studies published in early 2025 turn this picture on its head. Two independent investigations, one a cutting-edge computer simulation and the other a novel laboratory experiment, reveal that not only might smaller stars have formed in the ancient universe, but the chemistry enabling their birth could have been more dynamic and widespread than previously thought. One study simulated how turbulence inside vast clouds of primordial gas could cause them to fragment into smaller clumps, each capable of birthing a lower-mass star instead of just massive ones. The other experiment uncovered surprising details about molecular hydrogen, the critical coolant that allows gas clouds to collapse into stars, showing it may have formed earlier and in far greater quantities than expected, thanks to a chemical catalyst that might astonish even chemistry educators. As an astronomer specializing in star and planet formation with a keen interest in the chemical processes involved, I'm thrilled by the prospect that the first 50 to 100 million years after the Big Bang may have been a much busier and chemically rich era than we imagined. This could mean the second generation of stars, the oldest we can currently observe, and potential hosts of the very first planets, appeared sooner than we've believed. So how did those primordial stars form? Stars begin their lives inside massive clouds of hydrogen gas, sometimes spanning light years. These clouds collapse under their own gravity until the central region becomes hot and dense enough to ignite nuclear fusion, the process powering stars by fusing lighter atoms into heavier ones and releasing enormous amounts of energy. In the first stars, hydrogen fused into helium, causing them to shine brightly. The light we see from stars is just the surface glow fueled by energy generated deep in their cores. The total energy these stars emit is called luminosity. Over time, through a chain of fusion reactions called stellar nucleosynthesis, stars create heavier elements, carbon, oxygen, nitrogen, and up to iron, before ending their lives dramatically in supernova explosions. Those explosions produce even heavier elements found throughout the universe today. Massive stars burn brighter and exhaust their fuel faster, sometimes living only a few million years. In contrast, smaller stars, less than twice the mass of our sun, burn more slowly and can survive for billions or even trillions of years. If all early stars were massive, they would have long ago exploded and vanished. But if smaller stars formed then, some could still exist for us to find. But how do gas clouds cool enough to collapse into stars, especially smaller ones? Early protostellar clouds were warm, roughly at room temperature, meaning the internal gas pressure pushed outward, resisting collapse, much like the hot air inside a balloon keeps it inflated. If that heat dissipates, the gas loses pressure, enabling gravity to pull the cloud inward. Hydrogen and helium atoms aren't good at losing heat through radiation at low temperatures, but molecular hydrogen, H2, is excellent at this, emitting infrared light that cools the gas. For years, scientists assumed early clouds had too little H2 to cool efficiently, resulting in only massive stars forming. But the discovery that the molecule helium hydride, HEH+, once thought impossible due to helium's reputation as a non-reactive noble gas, could be more abundant than expected, changes the game. HEH+ helps produce molecular hydrogen and also acts as a coolant, releasing heat as light that lowers gas pressure. Adding another layer, turbulence or chaotic motion within these primordial gas clouds can break them into smaller fragments that eventually form lower mass stars. One recent simulation showed that turbulence could produce stars ranging from solar mass to 40 times heavier, meaning the full range of stellar sizes might have been present from the universe's infancy. These fresh insights challenge the old narrative of a universe initially dominated exclusively by giant stars, and open the exciting possibility that some lower-mass relic stars from the dawn of time might still be out there, waiting for astronomers to spot them. Detecting these faint, dim stars is extremely challenging, but ongoing searches are gradually pushing the limits of our instruments. And this is the part most people miss. If these lower-mass primordial stars do exist, they could hold priceless information about the early universe's chemistry and the very beginnings of planet formation. But do you think these new findings truly overturn decades of astronomical assumptions? Or could the reality be more nuanced? Share your thoughts. Could we soon rewrite the cosmic origin story of stars and planets? Or are we caught in an intriguing but incomplete puzzle?